Recording in progress.
Okay. Yes. Okay. Yes. Yes, so I think we should start at 2:00. Yeah. My name is Shandor Varro, and it's a pleasure to chair this session of seminar 2. Our first speaker is Professor Giuseppe Sansone from University of Freiburg, who would talk about attosecond science using free electron lasers. So please, Giuseppe.
So thanks a lot, Shandor, for the introduction, and also thanks a lot to the organizer for the invitation. I can start sharing my screen, and I hope you can see it now. Okay.
Yes.
Perfect. So as Sandor anticipated, I will talk about attosecond science using free electron laser. I have to point out, I will mostly focus on the experiments that we are currently doing with the seeded free electron laser. So I will not talk, very general of the science that can be done with free electron laser also operating in the SASE regime. So this will be the first point that I will address, how we can generate attosecond pulses using a seeded free electron laser. And then I will continue with some recent results we have obtained in the development of an attosecond timing tool with an excellent time resolution, and how we have used this attosecond timing tool to perform coherent control experiments in the two-color photoionization. So the laser that we are using, we are very happy users of the seeded free electron laser Fermi-3S. This laser can produce pulses in the X-ray and in the soft X-ray, and the peculiarity is that the process is not started by spontaneous emission as in other free electron laser. The generation of X-UV light is not started by spontaneous emission, but there is a seeding laser, which is typically a UV laser. So the third harmonic of a titanium sapphire laser system. This gives the possibility to obtain pulses which are longitudinally coherent, and also to synthesize harmonics of the fundamental field which are coherent with each other. And here you can see plots of a typical spectrum that we can use in our experiments, where we have 3 different harmonics. We can also synthesize 4 harmonics with excellent stability from shot to shot. Here you can see the typical values. We have a stability of the intensity of the single harmonic, which is on the order of few percent, 5–6%. So the first question that we ask ourselves when we started this kind of experiment is whether there was a way, to measure the relative phase between these harmonics, or if you prefer in an equivalent way, if there was a way to demonstrate that we are really synthesizing attosecond pulses with these harmonics. So what we did was essentially to go back to what is well known in the attosecond community using high-order harmonic generation and try to perform a so-called rabbit experiment. So a cross-correlation between the harmonics generated by the free electron laser and an infrared pulse. When you try to directly extend that approach to Fermi, the first problem that we had to fix, to solve, or to address at least, was the fact that while in rabbit we always consider the exchange of one photon with the IR field, this will not work at Fermi, because the distance in energy between consecutive harmonics is 3 times an infrared photon. These are harmonics of the UV laser of the third harmonic, so you need 3 IR photons at least to bridge the gap between 2 harmonics. So we could not work in the 10 to the 11 watts per centimeter square regime. We had to crank up the intensity in order to allow also the exchange of at least 2 IR photons. with the infrared field. This is at the end, let's say, a minor difference, because it's possible to show using strong field theory, the simulation based on the strong field approximation, that also in this case, we would expect to see oscillation of the so-called sidebands. So the sideband, the photoelectron peaks created by the absorption of one XUV photon and one or two infrared photon. And from these oscillation, it's possible to extract the phase difference. So the approach should work, provided that we can crank up the intensity of the IR up to 10 to the 12. What is also possible to easily show using the strong field approximation is that the sidebands, in this case, the two consecutive sidebands, oscillate, are composed by a constant factor and an oscillating part. And in the next part of the talk, I will indicate with P this oscillating part. Actually, the real problem that we had to address in extending the rabbit to Fermi was not so much the IR intensity, but rather let's say an intrinsic limitation of all free electron laser, which is the synchronization between the XUV or soft X-ray pulse and what is usually called the user laser. Can be an infrared pulse or a visible one. At Fermi, this stability is excellent, but this is still on the order of plus minus 3 femtoseconds. So if you look just to the simulation here on the left, you will immediately recognize that with an instability of plus minus 3 femtoseconds, you completely wash out the periodic sideband oscillation. So you will not be able to see this nice modulation of the sideband because you don't have control over this delay. And this is what essentially on the right you see represented, what you will see actually, just a noise. So random fluctuations of the intensity as a function of the shot number. But actually the interesting thing is that from this noise, which I would like to call a beautiful noise, we can get exactly the same information that we can retrieve looking to the periodic evolution of the sidebands. And I will show you in the next slide how we can still retrieve from this apparently noise the group delay dispersion of the harmonics, which is the key quantity in order to reconstruct the temporal profile of the pulses. So the key idea, it's the following. We replace essentially the control over the relative delay between the attosecond waveform and the infrared with a correlated analysis of the single shot photoelectron spectra. So because of the high photon flux available at all free electron laser, we can measure single shot photoelectron spectra. And then what we do, we construct correlation maps where we plot the oscillating part of one sideband, for example, the sidebands between harmonic 7 and 8, with respect to the oscillating components between another group of harmonics, in this case 8 and 9. So just to show you why this plot can give us access to the group delay dispersion, I will show you a few simulations. The first one is being obtained considering three harmonics perfectly in phase. We have the typical delay jitter at Fermi, plus minus 3 femtoseconds. And now if we imagine to run our experiments, this is what we will see. We will see that the sidebands, these two and these other two, have an oscillating component which is changing from shot to shot, but perfectly in phase with each other. So in other words, the correlation plot will show a perfect positive correlation equal to 1. We can also perform other simulation where, for example, the central harmonic now has a phase difference of pi over 2, and the correlation plot that we will get now, it's represented by a perfect circle. The last interesting, let's say, noteworthy case is when the phase of one harmonic, harmonic 7, is equal to pi, because in this case, we expect to see a perfect negative correlation. So a correlation coefficient equal to -1. We can easily run simulation with all possible phase differences, and what one can show easily, also using the strong field, is that the general form of this correlation plot is an ellipse. So what I was showing you before are 3 particular cases, but the key message is that the shape of the correlation plot depends on the phase difference of the phase difference. It depends on the second order phase difference between a group of 3 harmonics. So if you look now to this expression, you immediately recognize that what we have here is proportional to the group delay dispersion of the harmonic. So just by looking to the correlation plot, we can know which the group delay dispersion of the free harmonics is. So we performed the experiments at Fermi, where we just starting with free harmonics. So the Fermi has 6 ondulators available. Each harmonic was created by 2 consecutive ondulators, harmonic 9, 8, and 7. And we have, of course, and this is the great flexibility of free electron laser, to change also the relative phase between the different harmonics by using phase shifter here, which can delay the electron bunch going from the second ondulator to the third ondulator. And this corresponds to a change of the relative phase between the harmonics. The rest of the setup, let's say the final part, looks very similar to the classical attosecond pump probe experiments based on high-order harmonic source. So we have drilled mirrors through which the XUV pulse is propagating. An infrared pulse will be reflected by these drilled mirrors, and the two will be collinearly focused inside an interaction region where we place a magnetic bottle electron spectrometer in order to efficiently collect the photoelectron created in the two-color photoionization. I can show you the measurements here. You can see the summary of the experimental data where we present the correlation plot as a function of the relative of the phase of the harmonic 9, essentially. And you can see that we can clearly affect the correlation plot going from positive correlation to a circle, means that the group delay, the phase difference, the second order phase difference is equal to pi over 2. We go to negative correlation, and then if we keep going, increasing the delay, we will going back again to positive correlation. So these measurements gives directly access to the group delay dispersion, and this is the quantity that we need in order to reconstruct the attosecond pulse train. Now, the interesting point is that because we can generate the harmonics independently in different ondulators, and because we have access to the relative phase between each pairs of harmonic, we can perform a complete attosecond pulse shaping of the attosecond waveform. In particular, what we can do is we can decide whether we want to shape only the phase or only on the amplitude of the attosecond pulse train. Here you can see, for example, one measurement where, without affecting the intensity of the single harmonics, you can see here we have 3 spectra which are almost impossible, very difficult to recognize from each other. We change the relative phase, and this is, of course, affecting the attosecond waveform. We can go from a very nice attosecond pulse train to, let's say, what we will call not so nice, a red ugly attosecond pulse train here. We can also do the opposite pulse shaping, a pure amplitude shaping. So we don't change the phase between the harmonics. We keep this, in this case, to the best condition for the shortest attosecond pulse, group delay dispersion equal to 0, but we just affect the intensity of one selected harmonic. For example, for the blue one, we could increase the harmonic 9. For the red one, we were depressing the harmonic 7. Yeah, so we perform also a complete amplitude shaping here. One important characteristic, let's say, or byproduct of these experiments is that what we immediately realize that these correlation plots that we have could be also used to perform to create or to suggest an attosecond timing tool. So a way to reorder the single shot experimental data according to the relative phase between the attosecond waveform and the infrared field that you can see here. So, and I will show you now a movie showing the idea, but essentially what you will see is that the delay between these two pulses, which is changing. This is the simulated photoelectron spectra with the 4 sidebands between the harmonic 7, 8, and 9. And here the correlation plot. We fix the phase difference to minus pi over 2. So what we expect to see is a correlation plot which is given by circle. And what you can see, I hope you can see this now, you see that when we change the relative delay between the attosecond waveform and infrared field, the sideband spectra is of course changing, but you see that in the correlation plot, also the position of the single shot experimental point is also varying along a circle. In particular, for this group delay dispersion, there is a linear mapping between the phase, 3 omega, IR times tau, and the angle in the correlation plot. So there is really a straightforward mapping of the relative phase on the angle of the correlation plot. And we have exploited these characteristics in order to reorder the experimental data, and you can see here the results. So we have the correlation plot for the case of group delay dispersion equal to pi over 2 or minus pi over 2. This is not playing a major role, just a sign difference, also in the time arrow. But the important point is that we can reconstruct the sideband oscillation. You can see here these two sidebands which oscillate, or the periodic variation, better to say, and you can also see here the cutout of these sidebands, which is varying in time as expected. It's interesting to observe that the resolution that we can get in the estimation of the single shot, it's very small. It's just on the order of the atomic unit of time. We have an even smaller error if we want to determine the phase of the oscillation of one sideband. So not the experiment, the single experimental point, but the full phase oscillation. And then we have decided to try to use this attosecond timing tool for some experiments based on these two colors. So this was just a proof of principle that the technique is working. We can reorder the experimental point, and then we try to perform a coherent control experiments on the attosecond time scale using the capability of the attosecond timing tool. And I will try to explain you our idea. The first observation that I would like to do is that already the generation of sidebands, it's a coherent control experiment by itself. I mean, we are not describing in this way, but it's clearly a coherent control experiment in which we have two different pathways contributing to the sideband signal here. Sideband minus between 7/8, sideband plus 7/8. And each of these two sidebands can be generated either by the absorption of one photon of the harmonic 7 plus 1 or 2 IR photons, or by the absorption of one photon of the harmonic 8 minus 1 or 2 IR photons. By changing the delay between these two, between the IR and the attosecond waveform, we change the relative phase between these two paths, and that's why we see the oscillation of the sideband intensity. Now, with the capability offered by Fermi, we wanted to explore the possibility to add additional harmonics, for example, harmonic 6, to these three harmonics, and to increase the intensity up to the point where we don't allow only 2 IR photon transition, but we can observe 4 and even 5 IR photon transition. So in other words, we can generate these two sidebands, also starting for the harmonic 6. And the question that we pose ourselves were, can we control the amplitude of these two sidebands using the phase of the harmonic 6? And also, can we control the phase of the oscillation of these two sidebands controlling the phase of the harmonic 6? This is something that is not possible, that cannot be done with higher order harmonic sources, because we don't have the control of the phase of a single harmonic, but this can be done at the seeded free electron laser, Fermi. I will not go through the details of the SFA, but essentially what one can easily show is that the amplitude of the sidebands can be expressed in this way. And so we can quantify our capability to control the amplitude and the phase introducing these two parameters here. Delta S relative, because it's a normalized amplitude variation. So we have the amplitude of the sidebands minus the average amplitude of the sidebands divided by the average amplitude. And then the phase control, it's this additional term here, which appears in the cosine oscillation. Of course, if this picture is correct, we expect to see a dependence on the phase of the harmonic 6. And when you do, I mean, the derivation, you will immediately see that also in this case, what really matters is not really the phase of the harmonic 6, but rather the second order phase difference between the harmonic 6, 7, and 8. So we have again this phase difference of the phase difference. I can just show you now the experimental results that we have obtained a radar high near infrared intensity, so 4.2 to the 410 to the 12. This is quite high, I would say, it's very high for a rabbit measurement. In our case, because we want to have 4 and 5 IR transition, we must work in this regime. And here you can see the results on black for the sideband minus 7, 8, so the sideband closer to the harmonic 7, and here for the sideband plus, so the one closer to the harmonic 8. You can immediately recognize that we can control both the amplitude and the phase offset for both sidebands. But the variation of these sidebands, the variation of the amplitude and of the phase, I mean, it's following really a periodic curves. In the case of the sideband minus, we have a cosine here. In the case, maybe I can use a pointer. We have sideband minus here, the amplitude. For the phase offset here, we are following a minus sine curve. For the sideband plus, also, we have a minus cosine, and for the phase of the sideband, we have a sine. So the experimental points are indicated by circle and square. What you have at the dashed line, it's a sinusoidal fit of the experimental point. So you can clearly see that the fits, it's well reproduced in the data. And also for us, what was very important is that the theoretical prediction based on the time-dependent Schrödinger equation, this is the continuous curve, are perfectly matching. There is an excellent agreement with the sinusoidal fit of our experimental data. So we can, first of all, we can control this measurement so that we can really control the amplitude, we can control the phase, and we have excellent agreement also with theoretical model. The degree of amplitude control is rather large. It's on the order of 15%, 20%. And also what is very interesting, I think it's the control in the phase here corresponds in time to a control of just few attoseconds or few tenths of attosecond. You can see here the scale is going from minus 28 to 28 attoseconds. So again, in order to understand why we have this particular combination of cosine and sine, we can use the strong field model, the strong field approximation, which is, I think, very powerful in order to get this physical insight in these processes. Now, what is possible to show using the SFA is that the amplitude of the variation can be expressed as the sum of two terms, which we indicate here with B and C. So the term B, it's nothing else than the interfering term due to 1 and 2 near-infrared photon transition. So if you have the sideband minus, the B term will be given by the interference between the classical, let's say, or the usual two paths, harmonic 7 plus 1 IR photon, harmonic 8 minus 2 IR photon. The same for the sideband plus here. It's useful to represent now the sum of these two contribution in a complex plane. So B here has only a real part, so will be oriented along the x-axis here. We have the minus sign for the sideband minus, the positive sign for the sideband plus. The second term, which appears here, the term C in red, it's due to the interference between one photon of the harmonic 7 plus 1 IR photon, and then the path contributed by the harmonic 6 here. This will also oscillate at frequency 3 omega. An analogous one we have for the sideband plus. Harmonic 7 plus 2 IR photons and harmonic 6 plus 5 IR photons. The interesting point is that, and now you understand why it's useful to use the complex representation, is that in the complex plane, these two vectors, these two contributions will form an angle which depends essentially on the second order phase difference, so on the phase of the harmonic 6. The resulting amplitude is given by the sum of the two. So we have these vectors S minus and this vector S plus, And the amplitude control, it's essentially related to how the length of this vector is changing when we change the phase of the harmonic 6. And the phase control, it's related to this angle, delta K minus here. The same also for the sideband plus the length and the phase offset. So once we have this picture, we can, and I will show you another simulation now, you can easily see how the correlation between the different variation is connected to each other. So I will let now the phase difference 6, 7, 8 run from minus 3 half pi to pi half, and you can see how the length of the two vectors will change and also the corresponding angle. Here on the right, you will see how the amplitude of the sidebands is changing, and here also how the phase offset is changing. You see, we change the phase. This means that we are rotating the two vectors C minus and C plus, and this corresponds to a variation of the length and of the angle of the two vectors. And you immediately see that we can nicely reproduce the cosine and minus cosine oscillation for the amplitude, and also the sine and minus sine oscillation for the phase offset of the sidebands. So the SFA is very powerful in understanding what's going on. I mean, how we can coherently control the generation of the sidebands. And also from the derivation, one immediately sees that the degree of control depends on the ratio of these two terms between the two interfering terms. Now, what is the minor drawback, at least we think of the SFA, is that we can get a very good qualitative agreement, but not so a very good quantitative agreement with our experiments. Where we get, I mean, almost a perfect and excellent quantitative agreement with the TDSC simulation, because we can extract from the TDSC and the SFA the ratio of these two contributions, the modulus, and you can see that between experiments and TDSC, we have a very nice agreement. We have within the error bar apart from delta K minus, but we are radar off for the SFA. So we believe that the SFA in this intensity range is overestimating the contribution of the high order near infrared transition, and that's why the ratio it's not compatible, it's not consistent with our experimental data. I would like to arrive to the conclusion. So of course, all these experiments are done in large collaboration. So I would like to thank in particular the whole Fermi team, which has been really fantastic in all the experiments that we have done there. And in particular, also Praveen Kumar Maroju, who did his PhD and part of his postdoc in my group, and now is at University of Lund. And of course, I would like to thank you for your attention.
Okay, thank you very much, Giuseppe, for this excellent, highly interesting talk. And now I'm asking the participants whether someone had a question concerning. Yes, Mihail Yabikin, please. That was the first. Mikhail, yes. Pose your question.
Yes. About process.
I'm sorry, but we cannot hear you. So practically, we cannot hear you. Let's move to Barry Walker. Please pose your question, and then.
Great, thank you. Thank you for a very nice talk. The TDSC still has approximations in it, of course, and so I just wanted to clarify what those were. And I think they are a frozen core and a single active outside electron, which basically doesn't interact with the core, doesn't involve the electron correlation, but just has this one outer electron that's, or maybe it's higher order, maybe it Hartree-Fock interacts back with the core. I don't know. So I was going to ask about clarifications on that model.
No, the TDSC are a single active electron approximation. We are doing this in the single active electron. So as far as I know, it's a frozen core, but this is still good enough, let's say, for reproducing our experimental data.
Yeah, it's also important, I think, in terms of the understanding of the physics, right, to say that you can make this approximation and not even have that outer electron re-interact in a Hartree or Hartree-Fock way with the core, that it's basically out there with the field by itself. So, okay, thank you. I appreciate it.
Okay, let's go back to Mikhail. Perhaps your microphone is better now, functioning. Mikhail, please pose your question again, because we did not hear properly what you said. Well, it doesn't seem. Yeah, I'm awfully sorry, but I cannot hear. So let's see.
Mikhail could write his question into the chat.
I see. Okay. So still someone else to. Could you please write your question to the chat so that we can read it and then we can understand, because somehow your audio is not in shape. Well, I think in order to not to, I think if someone else would have a question, then please pose that. And if not, I think the best is to proceed, because I cannot see in the chat Mikhail's question. Okay. So I think, yes. No.
Does my microphone work?
There is an echo and so on. So it is practically do not understandable. Is this thing. Okay, let's. I think I propose to continue with the next talk. So, and maybe at the end of the session you could. No, yes, this is Dr. Antonov. So, Dr. Antonov will talk about attosecond perspective of plasma-based X-ray lasers. So, please. Please unmute. As I see, your mic is not unmuted. Unmute, please, your microphone. Otherwise, we can see.
Does it look?
Nice photo.
Yes, we hear you.
Now that's fine. Now we can hear. You.
First of all, I would
Please.
like to thank the organizers of the conference for giving me an opportunity to present this talk. And in this talk, we discuss the possibilities to use plasma-based X-ray lasers for the amplification and generation of attosecond signals. This work was done together with Elias Hayrulin and Mikhail Rybikin, and I would like also to thank our former collaborators, Olga Kocharovskaya, Simon Sukever, Jorge Roca, Mark Beryl, and Vyacheslav Shelevtsev. There are two basic pumping schemes of laser-pumped soft X-ray lasers. The first scheme implies collision or excitation of nickel-like or neon-like ions by hot electrons. This collisional pumping scheme allows to produce high energy radiation in the microjoule level at approximately 10 nanometer wavelength, and it is quite experimentally robust. That is why this is the most popular scheme. The other scheme is based on complete ionization of the medium and subsequent recombination of the plasma to the excited states of hydrogen-like or helium-like ions. And this recombination scheme allows to produce radiation with shorter wavelengths down to 4 or even 3 nanometers and requires less pumping energy. But this scheme is less robust and less popular. In our talk, we'll discuss both these schemes. And it is well known that a plasma-based X-ray laser can be seeded with high harmonic radiation of an optical laser field. Such seeding allows to considerably improve the spatial coherence of the output radiation and to slightly reduce its duration. However, the duration of the amplified signal still is governed by the gain bandwidth of an X-ray laser and lies in the sub-picosecond range. And typically, the gain bandwidth of an X-ray laser is much narrower than the frequency separation between the adjacent harmonics. And that is why the X-ray laser selects a single harmonic resonant to the inverted transition from the high harmonic signal. And it is it cannot amplify other second signals which are constituted by sets of harmonics. And in order to solve this problem, in order to amplify other second signals, the gain bandwidth of a plasma-based X-ray laser should be increased by several, from 2 to 4 orders of magnitude. And in our recent papers, we suggest a solution of this problem. And let us start the discussion with the case of linearly polarized high harmonics and hydrogen-like carbon 5+ recombination plasma-based X-ray laser. In the case of a hydrogen-like active medium, the population inversion is achieved at the transition between the first excited energy level and the ground state of the ions. We suggest to irradiate such an active medium with a combination of the fundamental frequency laser field and a set of its high-order harmonics. Both the laser field and the harmonics propagate along x-axis, which is the axis of the plasma channel. They overlap in space and time inside the active medium, and both these fields are linearly polarized along the same z-axis. Under the action of a strong laser field, the excited energy level of the ions, which is initially 4 times degenerate, is split into 3 sublevels. 2 of them correspond to the states 2 and 3, and these states experience linear stack shift. And the stack shift results in oscillation of the energies of these states in space and time at the laser frequency. These oscillations follow oscillations of the laser field strands. The transitions from these states to the ground state of the ions are responsible for the amplification of that polarized component of the X-ray field. That is for the amplification of harmonics. The remaining third sublevel corresponds to the states 4 and 5. And these states experience only a tiny quadratic stack shift under the action of the laser field. And thus, they are practically not modulated. And the transitions from these states to the ground state of the ions are the source of amplified spontaneous emission with Y polarization, with the polarization orthogonal to the polarization of harmonics. And space-time variation of energies of the states 2 and 3 result in a redistribution of the gain for the polarization component of the X-ray field from the frequency of the inverted transition to a set of sidebands. And these sidebands are separated from each other by the laser frequency. At the same time, since the states 4 and 5 are practically not modulated, the gain for Y polarization component of the X-ray field in the hydrogen-like active medium remains localized at a single transition frequency, which is, however, a little bit shifted from the amplitude frequency by the quadratic stack effect. And in this case, if some harmonic from the Sidon field is tuned in resonance with the central gain line for that polarized component of the X-ray field, then the other harmonics will be automatically resonant with the gain lines of even orders. And this fact allows for joint amplification of all the set of harmonics. But since the gain for Y polarization is not redistributed to the sidebands, the peak gain for the amplified spontaneous emission is several times higher than the peak gain for the harmonics. And in order to suppress the amplified spontaneous emission, one should use a sufficiently strong Sidon field in the considered case of hydrogen-like active medium. The gain coefficients for the harmonics are determined by squared Bessel functions of the modulation index, where the modulation index is a ratio between the amplitude of linear stack shift induced by the Wasser field and the Wasser frequency. As we show on the next slide, for some particular values of the modulation index, the gain coefficients for the harmonics of different orders have comparable magnitudes. And thus, these particular values of the modulation index are favorable for the amplification of harmonics with approximate preservation of their relative amplitudes. At the same time, usually the active medium of an X-ray laser is strongly dispersive for the modulating optical field. And in this case, the harmonics of different orders are amplified independently of each other. And the relative phases of the harmonics are also preserved. And if both the phases and the amplitudes of the harmonics are preserved during the amplification process, then the shape and duration of the second signals, which are produced by these sets of harmonics, are also approximately preserved. And in the following two slides, we show the results of calculations for the amplification of a set of 7 harmonics and a set of 21 harmonics of the modulating field. And we see that indeed the pulses nearly maintain the shape, and that the pulse can be sufficiently short on the order of 100 attoseconds. And let us turn to the more practical case of collisional neon-like X-ray laser. In this case, the main difference between the neon-like active medium and the hydrogen-like active medium is the absence of linear stack effect for neon-like ions. In the case of neon-like ions, all the Leysen states of the active medium experience quadratic stack shift. However, contrary to the case of hydrogen-like ions, this quadratic stack shift can be large as compared to the laser frequency. And that is why it should be taken into account as a space-time dependent value. And due to the quadratic stack shift, the energies of all Leysen states of neon-like ions oscillate in space and time with twice the laser frequency. And since all the states are modulated by the laser field, the gain in this case is redistributed to sets of sidebands for both polarization components of the X-ray field, both for Z polarization, which is the polarization of the laser field, and the laser field here is also linearly polarized as well as in the case of hydrogen-like ions. And for the orthogonal polarization, the gain is also redistributed to sidebands. And this fact promises the possibility for the amplification of elliptically polarized harmonics. However, in general, the gain lines for Z and Y polarization are mismatched. And this mismatch originates from the fact that the amplitudes of quadratic stack shifts of the states which are responsible for the amplification of Z and Y polarization components of the field, the amplitudes of these quadratic stack shifts are different. And this difference, in general case, prevents from amplification of Z and Y polarization components jointly. However, fortunately, this mismatch can be compensated via proper choice of the laser intensity. If we make this detuning between the gain lines equal to the frequency separation between the adjacent gain lines via proper choice of the laser intensity, then the CAS, sorry, could you stop your sharing of the screen? I see the screen of the next speaker, I guess. Так. Do you see my screen?
Yes,
Okay.
we can see.
And if the gain lines are matched, then the CAS gain line for the polarization overlaps with the gain line number K-1 for Y polarization. And in such a case, there are two distinct regions in the resulting spectrum. On the left wing of the spectrum, the gain for Z and Y polarization is practically the same. And here we plot half sum of the gain coefficients for Z and Y polarization on the top of the figure and the normalized difference between the gain coefficients on the bottom. And if we tune harmonics in resonance with these gain lines, the set of harmonics will be amplified with approximate preservation of the polarization state. And we test this case with a set of 5 harmonics with circular polarization. And we show that after amplification in a 1 centimeter long active medium, the energy of harmonics increases by 35 times at the cost of ellipticity decrease just by 11%. And the shape of pulses, individual pulse produced by this set of harmonics, the shape of this pulse is nearly preserved. And on the other hand, in the center of the gain spectrum, the gain considerably differs for Z and Y polarization. And for the gain lines marked by blue circles, the gain for Y polarization is larger. And if at the entrance to the medium we have a field with stronger elliptically polarized field with stronger Z polarization component, then at the optimal propagation distance we can amplify Y polarization to the level of Z polarization, and as a result the ellipticity of the output field will be close to unity at the peak of the intensity envelope. I mean, this coincidence of the peak of ellipticity and the peak of intensity is achieved for the optimal propagation distance. And again, the shape of individual pulse is nearly preserved during the amplification. But it is even more interesting to transform linearly polarized harmonics into circularly polarized, since the efficiency of harmonic generation is much higher for the case of linear polarization. And fortunately, it's possible to do this in the optically addressed neon-like active medium. And for this purpose, the gain lines for Z and Y polarization components should be a little bit mismatched by the proper choice of the modulating intensity. And then in between the gain lines, the amplification will be low, but the dispersion for Z and Y polarization components will be large, and it will have opposite signs. And here we show by red dotted curve the dispersion for Y polarization component, and by blue dotted curve the dispersion for Z polarization component. And if we have a linearly polarized harmonic at the entrance to the medium, which is oriented at a degree of 40 at an angle of 45 degrees with respect to the polarization of the laser field, then this harmonic will have both z projection to the z-axis and projection to the y-axis, and these components, z and y polarization components of the harmonic, will acquire opposite phase incursions during their propagation in the medium. And thus, at the optimal propagation distance, the phase incursion will be equal to pi over 2, and the polarization state of harmonic will become circular. And we checked that this approach works for the case of harmonics with finite bandwidth. In this case, however, the ellipticity, which is shown here by back curve, becomes time dependent. But again, at the optimal propagation distance, it's possible to make the ellipticity equal to unity at the peak of the intensity envelope of the output signal. And it is even more interesting that such effect can be observed for a set of harmonics. Though each harmonic is transformed from linearly polarized into circularly polarized at its own optimal propagation distance, it is always possible to find some propagation distance at which a set of harmonics will have a circular polarization at the time instance which correspond to maxima of sub-other cycle pulses produced by these harmonic sets. And we check it for the cases of a set of free harmonics, which is shown here, a set of 5 harmonics, 7 and 9 harmonics. And here, blue curve shows the intensity of the output signal, and red curve is the ellipticity. And what should be noted that this transformation is accompanied by harmonic amplification. It's possible to achieve a similar result with X-ray optics, but in that case, the efficiency of transformation will be on the order of few percent. And here we can make it with intensity increase. And the last part of short part of the talk is devoted to the spectral and temporal properties of amplified spontaneous emission of optically dressed X-ray lasers. And this work was done predominantly by Ilyas Hayrulin, and we show that the amplified spontaneous emission represents a train of sub-femtosecond bursts. And what is interesting is that the shape of the burst is fully deterministic. The stochastic nature of the amplified spontaneous emission affects only the amplitude of the burst. And thus we think that measurement of the spectra of such modulated soft X-ray laser can be the first step for the investigation of the discussed effect. I mean, it is the easiest experiment which can be done for starting this work. And instead of conclusion, I would like to mention advantages and disadvantages of collisional and recombination X-ray lasers for the attosecond pulse amplification. Collisional X-ray lasers possess negligible amplified spontaneous emission in the presence of high harmonic seed. It is the advantage. Another advantages are the possibility to amplify a set of elliptically polarized harmonics, robust operation, a high energy of radiation. The disadvantage is very high required intensity of the modulating field, strong plasma dispersion at the XUV wavelengths, which limits the minimum duration of the amplified pulse. And the comment, we studied only a few nickel-like ions and only one neon-like ions, and possibly we will achieve more interesting results if we consider more types of selective medium, and more theoretical efforts are needed to study this problem. As for the collisional X-ray lasers, I'm sorry, for the recombination X-ray lasers, advantages are more relaxed requirements on the intensity and energy of modulating infrared field, the possibility to amplify pulses with up to 100 attosecond duration, and shorter wavelengths of radiation. The disadvantages are the less robust scheme and strong amplified spontaneous emission of orthogonal polarization. And the comment that more experimental efforts are needed to build efficient recombination X-ray lasers. And thank you for your attention.
Okay. Thank you very much for this highly interesting and thorough presentation. And now I am asking whether someone would ask a question or comment or whatever. I myself would have one question. Your Bessel functions contain an argument, P omega.
Yes.
And as far as I remember, in the P omega, you have this D sub average. So it is something like, yes, D, yeah. What is the meaning of this? Because this is the work done of the IR electric field strength on the path length DAV divided by this photon energy light ticks. Now, what is this D? That's the question.
Yes, you correctly understood that this is the average dipole moment in the
average dipole moment
in the states 2 and 3, which are agent states of hydrogen like ion in parabolic coordinates. And these average dipole moments can be expressed through the dipole moment of transition between 2s and 2p states.
I see. Okay. Thank you. Has someone a question or a comment? I can't see. Then perhaps we proceed. So then please close your screen share. And we go on to the last speaker of this session, Dr. He, who will talk about double slit interferences in ion dynamics, in photo dissociation of molecules. So please, Dr. He, can start. Yes. Okay, we can see your screen. Nice, thank you. Please go on.
I need to point. Where is the point? Here. Can you see it? Can you see the point?
Yes, we can see the pointer.
Oh, okay. No, I think this is not. I think something wrong.
Yeah, but it moves slightly erratic.
So I think something is wrong with the point. So okay, I think now it's good. Yeah. So it's my pleasure today to have the opportunity to talk about our recent work on double slit interference in the ion dynamics of dissociative photoionization. So I will begin with a brief review of the double slit interference in the molecule photoionization. So in generally, in diatomic molecules, the photoelectron could be released from either from atom A or from atom B Thus, this will form a two-pathway interference. As a consequence, the photoelectromomentum distributions could exceed double-slit interference. This effect has been studied long ago since the pioneer work of Kohn and Fano. So below we depicted the typical photoelectromomentum distributions for the hydrogen atom and for hydrogen molecule ions when the photon is circularly polarized along the XY plane. So in the case of the atom, we can see that the momentum distribution is rotationally invariant. It's just a circle. While in the case of the hydrogen molecule ion, we see that there are multiple interference minimum due to the Young's double-slit interference. It is known that this kind of interference will depend on the parity of the initial state. For the 1s sigma g state, the ionization amplitude is proportional to the cosine function, while for the 2p sigma u state, the amplitude is proportional to the sine function, and this cosine and sine structure will be reflected in the nodal structure of the photoelectron distribution correspondingly. The double-slit interference in photoionization has been confirmed by extensive experiment. For example, in this work, this author has studied the single photon double ionization process, and they have found that for the fast electron, and the angular distribution present double-slit interference effect. And more recently, it's by utilizing the fringe shift due to the double-slit interference combined with the non-dipole effect. It has been found the time that the photon across the molecule bound length has been identified, which is determined to be 247 femtoseconds for the hydrogen molecule. Not only for the single photon ionization, but also in the tunneling ionization, the double-slit interference could play a role. In the case of the neon diamond, where the sigma g 2p orbits and the sigma u 2p orbits have nearly degenerate energies. So in this case, due to the mixing of the molecule orbits, one have the corresponding double-slit interference structures, and of course, the detail of the interference pattern will depend on the parity of the initial state. So far, we talked about the double-slit interference in the photoelectron. For the photoelectron, one natural has a question: what's the role of double-slit interference in the ion dynamics? Well, to answer this question, we need to understand how the photoelectron dynamics could affect the ion dynamics. This is known as the photoelectron recoil effect, and it was known that the photoelectron recoil could lead to the ion vibration. And in the theoretical description, it is usually assumed that the photoelectron recoil momentum localized at one of the atoms. And the vibrational energies increases with the photon energy because the recoil momentum is increasing with the photon energy, and thus effectively more high energy level of the vibrational state could be populated. Thus, the effective ionization energy increases due to the recoil momentum, and this is the vibration of the ion induced by the photoelectron recoil. The photoelectron recoil could also induce the ion rotation. For example, in this study, in the initial ionization of the nitrogen molecule is studied by high energy photons. The nitrogen molecule absorbs a high energy photon and gets ionized, and the populated the N2+ ion is nearly isotropic initially, but it rotates due to the populated rotational state, and then after some time, the populated the rotated N2 plus will decay while the oscillation process. As a consequence, one finally has two nitrogen ion plus one electron, and it is worth noting that the ion momentum distribution rotates compared to the initial isotropic distribution. So as far as we know, the double slit interference in the ion dynamics, especially in the case of the dissociated ion, has remained little bit explored, and as we will show, to have the double slit interference in the ion dynamics, the correlated electron plays a key role, and to explore the correlated dynamics of the photoelectron and the ion, we treat the process under the Born-Oppenheimer approximation. The molecule ionization amplitude is calculated by perturbation theory, while the subsequent nuclear motion is propagated via the Schrödinger equation numerically and is projected on the asymptotic momentum state and the end of propagation. Here, this M is the joint transition amplitude of the photoelectron and ion. The capital letter P represents the ion momentum, and the K represents the photoelectron momentum. The chi is the ion wave function. Chi is the initial wave function of the ion, and T is the ionization amplitude of the photoelectron. And this T is calculated via the first order perturbation theory. So apply this formalism. We began with the simplest molecule, the hydrogen molecule ion. The ground state of the hydrogen molecule is isotropic in space orientation, and the radial distribution is plotted here. It has a maximum value, and the internuclear distance are around 2 atomic units. So we are starting the process. Then the hydrogen molecule ion absorb one photon and gets ionized, and the remaining 2 protons experience the Coulomb explosion. Here is our numerical results. So in this panel A, we plot the joint energy spectrum of the photoelectron and the ion. So it is one single strip, and this reflects the energy conservation. By integrating out the kinetic energy release, we can obtain this panel E, and this is a spectrum for the photoelectron. One can see that this photoelectron spectrum has a maximum probability and E around omega minus IPRM. So this omega is the photon frequency, and the IP is the ionization energy and the nuclear displacement Rm. And so if we integrate out the photoelectron energy, then we get a spectrum for the kinetic energy release. And the kinetic energy release spectrum has a maximum and around 1/Rm. So these results are consistent with the consideration from the frozen core approximations. And so this is the first step. Then let's move to the ion momentum distributions. So here we consider the case that the emitting photoelectron is along the x-axis. Here, this white dashed line represents the K tilt. That's whose definition is equals the momentum of the electron minus the momentum of the photon, and the white dashed line is perpendicular to this K tilt. And as one can see, that this ion momentum distribution is symmetric with respect to this white dashed line, because for this ionization of the hydrogen molecule ion, we can see that the amplitude is proportional to this cosine function, and also because two ions have equal mass, the recoil momentum vanishes. So we have a symmetric ion distribution, and it is it is important to point out that to have double slit interference in the ion momentum distribution, it is necessary to fix the emitting direction of the photoelectron. So here, this left panel is the case that the photoelectron is along the x-axis, and the right panel is the case that we integrate out over the photoelectron emitting angles, and we can see that the double slit interference signal is not visible after integrating out the photoelectron emitting angle. This is an interesting analog to the case of the photoelectron double slit interference. And in the case when the two ions have different masses, then we can see that non-vanish recoil momentum will arise, and due to this non-vanish recoil momentum, then we have a deviation from a symmetry with respect to this white dashed line. A deflection of the ion momentum distribution is observed. This is because for isotopes, the recoil momentum is equally shared between the two nuclei, and the two nuclei acquire different velocity due to the different ion masses, which results in a non-vanishing relative momentum PR. And due to this non-vanishing momentum PR, we have this deflection of the photoelectron momentum distribution, ion momentum distribution. And it is not surprising that the detail of this interference ion momentum distribution will also depend on the parity of the initial state. For the dissociative channel of the hydrogen molecule, and the ionization amplitude is proportional to sign function, and so this we have a complement ion distribution compared to the case of the hydrogen molecule ion. So the results above, for the results above, we have averaged over the photoelectron energy. This corresponding to the average over the internuclear distance. So if we choose a specific value of the photoelectron energy, say let's use 19.1 atomic units. This will correspond to ionization happens and are around 3.1 atomic units. For this, the R times the K has a larger value, so one can say that one has more nodal structures along the in the angular distributions. However, if we choose the photoelectron energy to be 18.7 atomic units, and this will correspond to ionization from around 1.7 atomic units, and in this case, R times K is small, and so we have less nodal structure in the angular distribution. And it is also not surprising that one can tune the photo frequency to tune the angular distribution of the ion momentum distribution. This is because in this case the K times R is larger, and so we will have more and more nodal structures when the photon frequency increase. Apart from the angular distribution of the ion, it is also possible to observe the double slit interference via the longitudinal momentum shift of the ion. So here we calculate the ion momentum shift when the emitting angle of the photoelectron is half pi and a quarter of pi. Here, the black solid line is the case that we use the full form of the ionization amplitude, and the blue dashed line is the case that we do not include the double slit interference effect. And as we can see here, that compared to the white dashed line, one can see the oscillating structures along the solid black solid line. This is because for the different photoelectron energy, they are ionized from different internuclear distance. As a consequence, because R times K will be different, so the double slit interference is also different, and we will see the oscillation here. And then this red dotted dashed line is the case of the dipole theory, and we can see that in general this dipole theory will also have a non-valuation momentum shift, and this is because this longitudinal momentum shift comes from the recoil of the photoelectron, and the photon effect simply just increase the momentum shift a little bit. And so when we scan over the photoelectron emitting angle, the double slit interference is not apparent in this momentum shift, because this momentum shift is largely determined by the recoil momentum, which we can estimate via this cosine function, which is obtained by the recoil momentum, and the non-dipole effects will, as shown in this spectrum of the theta E distribution, it is simply will slightly change the emitting direction of the photoelectron, and the photoelectron is more likely to be emitted forwardly. And while the interesting point is that while the double slit interference is not observable in this theta E dependent term, but however, after integrating over this theta E dependence, we can it is amazing that this double slit oscillation is again observable. Here we integrate over the photoelectron degree of freedoms, and but then we change the frequency of the photon, and we can see that the oscillating structure appear, which is a typical double-slit interference pattern. Here, this black solid line is the case for the HT plus, and the blue dashed line is the case of HT, and the red dotted line is the case of HT plus, but in the dipole approximation. And we can estimate this behavior as from the recoil of the photoelectron, and we can see that this oscillation will depend crucially on the asymmetry of the ion mass, and also because the appearance of this kinetic energy over C structure, it means that this structure is essentially a non-dipole effect, and the correspondingly this J1 and J0 are the spherical Bessel function of the first kind, which are characteristic of the double slit interference. So we have shown that it is really possible for the ion to have double slit interference structures. And the next question is it possible to have some kind of application? So as an illustration, we consider the coherent control via the double slit interference using the double ionization as an example. For this purpose, we consider the palm-proof scheme. So in our scheme, we first have a palm pass to ionize the HT to the HT plus, and then we add a probe pass with a delay on TD, and the HT plus will be ionized by the second pass, and so as a consequence, the remaining H plus and D plus will experience the Coulomb explosion. the dynamics could be illustrated as below. So for the initially we have a ground state HT plus. It could observe one single photon to the 1s sigma g state, and this is the energy curve for the 1s sigma g state. It has a minimum Him, so it can admit the vibrational and rotational states. And so the populated 1s sigma g state will vibrate and rotate, and after the second pass arrive, it will observe another photon, and one has double ionization. And it is also possible that this ground state HT molecule could observe one photon to populate to the 2p sigma u state, and this state is not stable. It will dissociate directly, and then it could observe another photon from the probe path and to achieve double ionization. And this is all numerical results. We have plotted the joint energy spectrum of the two photoelectron. So one can see that the two photoelectron has maximum value at around this 19.35 atomic units and 80.775 atomic units, which corresponding to a case when the intermediate state HT plus is in the 1s sigma g and 2p sigma u state respectively. And so then we calculate the ion momentum distribution by fixing the direction of the first electron to be along the x-axis, and here we fix the time delay between the palm pass and the probe pass to be 1000 atomic units. And in this panel A, we plot the distribution for the 1s sigma g pathway, and this could be described by this cosine multiply cosine function, and this panel B corresponds to the 2p sigma u pathway, and this distribution could be described by this sine multiply sine function, and the panel C is the coherent summation. And from this coherent summation, coherent sum, we can see that the addition of the two pathway will lead to the interference structures, and one can see that when the overlap of the two pathway is negligible, the pathway information can be resolved via the emission angle of the entangled ion and the photoelectrons. And however, when the overlap is significant, then the pathway information is lost, but then the interference is significant in this case. And the interest point is that because we have an intermediate 1 sigma g state which could vibrate and rotate, so this dynamic information could be encoded in this interference pattern. To show this, we show this movie of the evolution of the ion. The left panel is the case with the recoil momentum, and the right panel is the case without the recoil momentum. Yes. So here are some snapshot of the movie. The upper panel is the case with the recoil momentum, and the lower panel is the case without the recoil momentum. As we can see that the recoil momentum will induce the rotation of the ion, while in the absence of the recoil momentum, the ion only vibrates and does not rotate, and the vibration is always there because this comes from the population of the Frank-Condon states, and only when the recoil momentum will induce the rotation of this ion bound state. And the information of this bound state is imprinted in the ion yields. So here we plot three curves when the time delay is 1000 atomic units and for the black solid line and the 2000 atomic units for the blue dashed line and the 3000 atomic units for the red dotted dashed line. As we can see that as a consequence of the two pathway interference, the M yield is maximum when the momentum of the two photoelectrons are parallel and due to the rotation, and this phi around 0.7 atomic units, gradually it develops to a local maximum point when the time delay is around 3000 atomic units. And the reason, and we can offer a simple explanation for why this parallel configuration is preferred. So because for the ionization amplitude, the ionization amplitude from two pathway could be written as this cosine multiply cosine function plus this sine plus multiply sine function. Because for our chosen parameter, so both the first term and the second term are both positive. So this will correspond then the addition will be the addition will be preferred. So thus we have a parallel emitting configuration. So here is the summary of my talk. We have demonstrated that double slit interference in the ion momentum distribution when the correlated photoelectron emission angle is fixed. And we have shown also that the double slit interference signature of the M survives in the average longitudinal momentum shift even when the correlated electron information is lost. The interference due to the photoelectron entanglement could serve as additional leverage for coherent control of molecule dynamics in dissociative photoanizations. And because for the molecule orbits have degenerate energies, in the strong field ionization, one can also have double slit interference. So these conclusions can be generalized to the case of strong field dissociative ionization when molecule orbits have degenerate energies. Then, thank you for your attention.
We are thanking you very much for this very interesting talk. And now let's see whether someone has a question concerning this presentation. Maybe I would ask one formal thing, certainly. You had an estimate where you used the spherical Bessel functions for the electrons. And now this is, of course, true and usable, yes, this. When you have short-range potentials, but so didn't you care about the long-range character of the Coulomb interaction, or is it immaterial?
So because the photon energy here is to be 20 atomic units, so in this case we think the Coulomb potential will play a minor role. So this estimation comes from only from the plane waves, and we think this long-range Coulomb factor will be negligible in this case.
Okay, thank you. Still, I am looking around whether someone.
I have a very simple question.
Yes, please.
A very nice talk, but I just want to make sure that I understand. So the maximum effect that you would see is when the electron wave function that you're ionizing, the molecular wave function that you're ionizing, is shared equally or between the two particular nuclei. So for example, if it was a core state, like you mentioned with the nitrogen, you really wouldn't see this sort of interference at all. Is that's correct?
So actually, this is not so trivial question. So because in the case of the nitrogen, so as you said, the core electron is deeply bounded inside the near the nuclear. So it could
and highly localized there. Yeah.
Yes, highly localized. So in fact, technically, so if in ideal consideration, you can still observe this double slit interference, but because you have a very small energy gap between this molecule orbits, so maybe some perturbation will destroy the coherence of the core electron. So it would be very hard to observe this double slit interference. But technically speaking, I believe there is still a parameter that you can observe this double slit interference even for the core electron.
Even though it's so highly localized that most of the scattering and interaction would be with one of the nuclei versus the other. Because it's a short range interaction, I think, right? I mean, it is a short range. Yeah. Okay. All right. Thank you. Very nice.
Okay. Is there some question or remark? Okay. If not, then I am thanking for all the speakers of the session, and we close the session. Bye.
Thank you. Thank you to the speakers, and thank you, Strandor.
Okay.
Goodbye.
Bye, Ranihan.